We've talked a lot about phasors in this class. Phasors, remember, were basically just two-dimensional vectors, and we would often have them rotating around in a plane. It turns out a nice way of describing what essentially amounts to phasors is complex numbers. The square root of a -1, we say, is equal to I. I for imaginary. This isn't a real number, it's an imaginary number. But it has well-defined properties that we can work with. Then I can take any number that is said to be a complex number if it has a real part and an imaginary part. So a plus ib. Notice both a and b are real numbers, but the entire number, sometimes called c, is complex because it has a real part and an imaginary part. We'll plot that in a plane at position A, B. So the imaginary part tends to be on the y-axis, the real part on the x-axis. Sometimes we want to talk about the magnitude of that complex number. That's how long this vector is in the complex plane. Well, clearly, that's just going to be the square root of a squared plus b squared. So if I wanted to know the magnitude of c squared, I write it as the absolute value of c squared, absolute value for magnitude, and then squared. That's a squared plus b squared. That's not the same as just taking c and multiplying it by itself. If I take c times c, well, that's a plus ib squared, which is a squared plus 2iab. When I square the ib, that actually becomes minus, because I is the square root of -1. So it's minus b squared. Notice that is very different from this term up here. So this is called the magnitude squared. And it turns out that that magnitude squared is equal to c, the complex number, times its complex conjugate, where complex conjugate simply means we take the imaginary part and change its sign. So this is a plus ib times a minus ib. We get a squared, we get a plus iba, we get a minus iba, and those two terms cancel, and then the I times I gives us a -1, the plus times negative gives us a -1, and we end up with a squared plus b squared, as we need to. Shrink all this, make that statement. The complex conjugate of c is a minus ib. A particularly useful complex number is e to the I theta. I'm not going to prove it right now, but e to the I theta, it turns out, has a cosine theta plus I sine theta. Essentially, it has a magnitude of 1, and it circles around in the complex plane. So if I have a magnitude of 1 and an angle theta, then the real part is just cosine theta, and the imaginary part is just sine of theta. This is convenient because all the mathematics of an exponential, which are much simpler than the mathematics of trig functions, still comes through. So for example, e to the I alpha times e to the I beta is equal to e to the I alpha plus beta, which is a much easier way of figuring out all your trig identities. You expand these in terms of cosine and sine, multiply them. You expand this in terms of cosine and sine, and suddenly you have your sum of cosines and sine of your sine of a sum and cosine of a sum formulas. It also means if we want this to be oscillating, we simply use not cosine omega t or sine omega t. We tend to use e to the I omega t to represent an oscillating function. Now, why do I go into all this complex number information? It turns out that our wave function for a particle can't be fully described if we try and make it strictly real. It is a complex quantity. And it's not that the probability is really proportional to the wave function squared. Turns out the probability is proportional to the absolute value of the wave function squared, or the wave function times its complex conjugate. So I introduce these basic ideas so that when I start talking about Schrodinger's equation, it's not completely foreign to you.